Okay. I mean, this is working, right?
First class. Yes.
Okay. Now. Great. Okay, so we finished last time with the superspace, and today we're going to discuss anything about superspace. I mentioned last time. Space. I'll remind where we finished last time. So basically, for our purposes, superspace is just the supergroup, which is the exponentiation of the our favorite algebra, which we slightly changing normalization now, right, like this. And the supergroup is the exponentiation. I will a little bit try to change some notation with the hope that I will get the right signs. This is not guaranteed. I mean, there is in this supersymmetric science, there's always some struggle with science. It's difficult to get them right. So the superfields are functions supergroup. So we will call them capital phi. So they depend on element G. G belongs to the supergroup. Or in more plain terms, it is just a function of these variables t and theta. And since theta is nilpotent, this can be expanded in finite series. In this case, it's just a series with two terms. One of t. So superfields can also have some grading, just like the theta variables or the t variable. So the grading, so the superfield is supposed to be homogeneous, grading wise. So if you know the grading of phi like this, so this should be the grading of 0. This should be the grading of phi 1 plus 1. So for example, I think, they will encounter both Grassmann odd and Grassmann even superfields. So for example, if phi is Grassmann even, so phi 0 is also Grassmann even, or what we call bosonic. Yes, and phi 1 is fermionic or Grassmann odd. And so therefore, all Grassmann odd guys, they anti-commute with theta. So the sign kind of matters here. Yeah, like I mentioned last time, these coefficients of the expansion in theta are called component fields. And this structure of superfields is basically similar for all n. So in higher n, we'll have more thetas. We'll have higher polynomials of higher degree.
Sorry, phi 1 commutes with theta. Always.
No, anti-commutes with theta. Anti-commutes with theta. Anti-commutes phi 1. No, I mean, it depends. So if phi is bosonic field, so degree 0, then this is degree 0, and this guy together is degree 0. So that means phi 1 is degree odd degree.
I see.
So it anti-commutes with theta. If it's this one is fermionic field, so this is fermionic, then this is bosonic, then commutes with theta. So yeah. So there is an action of our supergroup on such functions. So if we have some element G0 of G0 belongs to this supergroup, then we can act with it on our function by sending it to the function of a shifted argument. That G goes G0, G0, G. Or you mentioned it would be G0 inverse, right? Okay, let's follow. Let's try G0 inverse. G. Right. I guess the inverse is motivated by the fact that if you apply twice, you get a G1 inverse, G0 inverse, which is G0, G1 inverse. Yes. Compose this in the order. Okay, yeah, let's maybe write like this. It will change some signs formulas, but maybe it will be the right signs. So now we want to. So since we have the action of the group, we can also have the action of the Lie algebra by differentiating the action of the group, right? So we call the corresponding vector field. So the vector field corresponding to some generator, any generator, say H is d over ds. I mean, VH acting on phi. By definition, d over ds, phi of minus h times G0, so times G, s equals 0. And same for VQ. And so now we will parameterize the group element in the same way as before. So we want to compute this. So this is here is e to the minus sh, e to the minus I th plus theta q. This is e to the minus I minus is h plus theta q. So differentiating this, yeah, so that means that this d over ds is minus I times d phi over dt. Okay, and so the vector field, so it means that vector field dh is minus I d over dt. And more interestingly, we'll complete the action of q. So u I by the same formula minus s q into the th theta q at s equals 0. And so we should combine this using the Baker-Hausdorff formula. So by the Baker-Hausdorff formula, this is the exponent of the sum of these guys, minus sq q plus 1/2 times the commutator of sq commutator of sq. Maybe let us write this as d over d epsilon. So we will assume that epsilon is a Grassmann variable this time. What is that? Epsilon q. With th plus theta q. Plus higher order terms that are in this case 0. We have a nilpotent Lie algebra. super Lie algebra. Truncates after first commutator. Okay, so Q commutes with H, so this doesn't contribute. And then, so we'd like to write that this is minus I over 2 epsilon theta commutator of Q with Q. So this is 2H. Okay, and let's see what we get. So minus I, so this is minus so 2 cancel the 2, and then that minus I t plus epsilon theta H. Okay. So this should be then minus I d over d theta plus theta d over dt acting on phi. So I think this is what I wanted to get. So so our vector field VQ is this field here, VQ. And usually in this, just for simplified notation, it's just called Q. So it's called Q, meaning that Q is some differential operator in superspace. So, and you can easily check that it satisfies the property that Q squared is minus I d over dt equals H. It's true. Right, you get the square of each term is 0, and then you get the cross term, which is precisely the anti-commutator of theta with d over d theta. Okay, so this is the action of supercharging superspace, the action of the vector field, super vector field on functions, on superfields. And so the point is that how this, okay, so yeah, first I should also mention that there's also the right action of the, right? So we can, so right action. So you can send your function to a function of the right shifted. So with the action d0. And the right action also, first of all, the action of H is the same either from left or from right because it's a central element. And the action of Q will have a slight modification. So the if we take for G0 equals e to the SQ or epsilon Q, and then we write the right vector field, so we right Q, the same formula, d over d epsilon. By the way, when I write derivatives with respect to the Grassmann variable, I always mean left derivative, so I bring them to the left. So d over d epsilon of this guy. Then we will not care about the overall normalization in this case, but it would be some other vector fields that will differ from this one by sign here. So, and this vector field is called the superderivative. So, like I say, the overall factor will not bother us, but the expression for d will be important. So d is, by definition, is d over d theta minus I theta d over dt. If you multiply this with minus I, you will have exactly the opposite sign here. And so it has also the useful properties that, so yes, well, this is called superderivative. So first of all, d squared is also minus I d over dt. And moreover, d and q anti-commute. Well, this is because it's left and right action. So if you multiply it by the crossing parameters, they will commute. So, but you can also explicitly check it by commuting the operators. So how does this? Let's see how this these operators act on the superfield. Most importantly, we want the supersymmetry transformation properties of the superfields. So this is Q, and we will so the super variation of the any superfield is by definition is epsilon Q acting on that superfield. This is a variation of the variation with respect to supersymmetry transformations. And so we recall the expression for the superfield. So phi is 0 plus theta for 1. So that means you differentiate this guy. So this is minus I epsilon phi 1 plus theta plus epsilon theta by 0 dot. So in this case, we will we want to say that this is kind of obtained by variation of the component fields. So say that by definition, this is delta phi 0 plus theta delta phi 1. And from this, we can therefore find the variation of the component fields. So delta phi 0 is just equating coefficients in front of power of theta. Delta phi 0 is minus epsilon phi 1. Delta phi 1 is epsilon theta by 0 dot. So these kind of formulas are ubiquitous in supersymmetry. And the key, kind of one of the key properties is that in contrast to usual global symmetries that are that do not involve the Hamiltonian as part of the algebra, where just one field transforms into another field transforms into, say, a third field. This one involves derivatives. Okay? So the presence of derivatives is a benchmark of supersymmetric transformations. So okay. So out of the superfields, I mean, the reason that we introduced superfields is that we'd like to build supersymmetric actions or supersymmetric Lagrangians that we need for mechanics, for classical mechanics. So we want to ask, what about supersymmetric Lagrangians or action? So first of all, we may try. So we want to construct an invariant, right? Some function that is invariant with respect to Q. That's what we call supersymmetric function. So let's Lagrangian is some function of the fields, so let's suppose we have some superfields phi 1, phi m, and the Lagrangian is some local functions of a polynomial, let's say, or whatever local function of phi 1, phi m. And we want to ask if, and we want to require that such that action of Q vector field on L is 0. But in this case, acting on it twice, so Q squared L is 0. But on the other hand, this is minus I dl over dt. So it means that L is a constant. So that's not very good. And we can't have any invariant. That's not a constant. And by the way, when I write a partial derivative here, I mean partial derivative to differentiate it from the derivative with respect to theta. Of course, it doesn't mean that I'm not referring to some explicit time dependence. All time dependence is in the field, but it means with constant theta fixed. So how does one? The consequence of this is that actually there are no local supersymmetric invariants. But the way around it is that we can define quantities that shifts under the action of Q shifts by total time derivative. So one can construct supersymmetric actions. So the action, which is the integral of the Lagrangian over dt, will be invariant. How can we do that? Well, actually, we already see that. We can already see that from the variation. From the variation formulas that I've written here, right? That the variation of phi 1 is a total derivative. So total derivative. And what is phi 1? Phi 1. Phi 1 is the top component of a superfield. And this applies to any superfield, right? It doesn't have to be some fundamental superfield. It can be a polynomial superfield. Anyways, because Q affects by the Leibniz rule, Q is a differential operator. So if you take a say variation of some, if you compute the top component, say of some function L of your elementary fields, it will still shift by a total derivative. However, it will be a derivative of some composite expression here. So the way to construct supersymmetric actions is to take top components of some superfield. Top means the coefficients of theta. You take later on we'll have higher dimensional supersymmetry. That means top component of the expansion. It's always the top component of the expansion. That's kind of a general law of supersymmetry. So what you should take for L. L is so let's maybe call it L theta. So L theta is the top component. So the component L of phi1 the component of this guy. And so this theta component will always shift by derivative. And once we take the integral, this will be invariant, well, under suitable boundary conditions, but we assume that we always have some suitable boundary conditions. So we will always treat formally integrals of derivatives as being zero. So there are various notations for this top component. You can find in the literature. So first of all, you see, if you take a super derivative of any superfield, this is d over d theta minus I theta d over dt of phi 0 plus theta phi 1. So this is phi 1 minus I theta phi 0 dot, right? So the top component is phi 1. So so that means that phi 1 is just the super derivative of your superfield taken at theta equals 0. So you can take a derivative of your superfield and forget thetas, and this will be your top component. The other notation, colloquial notation, is by deriving integral, super integral. There's some kind of formal integral, which says that the integral of some superfield is by definition is derivative. So since phi is only linear in theta, the derivative is independent of theta. This is theta independent. Yeah, so for example, phi 1, therefore, the integral over your superfield phi over d theta in this notation. And well, the reason why this is maybe common notation is because then your actions will be integrals over superspace as well as over space time. So for example, then your action will be integral dt d theta of this L function of your some superfield L. So this is kind of how superspace actions look like. They're integrals over space-time, or in this case over time, because it's mechanics, and integral over superspace. Yeah, the useful, before we erase the superderivative, it is the useful property of the superderivative is that you can integrate by parts. It's because the integral of the superderivative is so the integral of the superderivative. The superderivative is written here, so the integral is minus I phi dot. So it's a time derivative. So that means if you integrate twice, this will be 0, right? I mean, if you integrate over time, this is 0. Just like I say, we treat integrals of derivatives as 0. So that means if you have superspace actions, you can integrate by parts. If you have super derivative there, So that's in Superspec. So the next question we want to address is so what kind of super Lagrangians should we consider? So there is this L here, which is a function of superfields. So what kind of function should it be? So that we have some reasonable mechanical action. Give us resemble less mechanics. So yeah, so for example, suppose we just take a first just take a fundamental field as our Lagrangian, and we write dt d theta. We already written somewhere dt d theta of phi. Then this is just integral over dt by 1 of t. So well, it's not very very interesting because it's it just gives some empty kind of well trivial equation if you want to take variation of this formal solution, right? So you could as well take for some polynomial as we suggested here, polynomial of phi's. For example, what if we take phi 1, phi 2, the product of two fields? But then, so the way you go about it, you expand this phi 1, 1, and similarly for this field. And but in the end, you get just some polynomial Lagrangians. 1, 1, 0, 2, 0, 1. And clearly this structure will pertain in many range local functions of the fields. But I mean, we want Lagrangians that have some derivative. So this way you don't get any derivatives. So yeah, by the way, one other way to see why this action is supersymmetric invariant is just to perform explicitly to take the variation, take variation of this guy, and the variation of this guy is dt d theta, and then you sum over, take the variation of all the fields entering the Lagrangian, so dl over d phi k, let's say delta phi k, and delta phi k is epsilon q phi k. But then you use the Leibniz rule, right? And you say that this is just epsilon q of L. And since we need to pick integration over theta picks the top component of this guy, so that means that this is I'll just write schematically, not caring about the size coefficient, and this is dt of d over dt, dl over dt. And this is 0. Right? Because Q, you should always remember the structure of Q, that Q is proportional to d over d theta plus something times theta d over dt. I mean, there's some coefficients here. Never mind. So when you pick a theta component, you pick the derivative. So so why do I recall this argument? I mean, the point is that the same argument will go through if we allow L to be a function not only of the fields, but also of their superderivatives. Phi 1, m, 1, and possibly also time derivative. So you can also have higher powers of d, but square of d is time derivative. So possibly higher powers, but then you want to usually in physical theories or in mechanics, we truncate to some no more than one derivative, let's say. So let's just assume it's like this. Because and the reason why, so if you take the variation of this guy, you have to differentiate with respect to these derivatives and take variation of the derivative. But the variation of the derivative is the same as it just comes from the variation of the field itself, right? So variation of the derivative is just d over epsilon q phi. And so this is epsilon q of d phi. Which means epsilon q still factorizes in front of the full guy, because q anti-commutes with d and epsilon anti-commutes with everything. So epsilon q commutes with d. So that's the main property why we need the superderivative. So it's you can act with it on the superfield, and you still get another superfield that you can use in your Lagrange. Okay, so then what would be so with these superderivatives, we can actually construct dynamical actions, actions that give some dynamical equation. So what would be the simplest model with derivatives? So maybe simplest model is the following. So we can take for our Lagrangian, maybe I'll write it purely Lagrangian. So I have the superspace Lagrangian L, and then when I integrate it over theta, I call it the usual. I'll call it L. So L is L, and this is the just integral of d theta phi bar d phi. And phi here is a complex superfield. So phi bar is complex conjugation. So this is a complex superfield. So once I define complex conjugation, I should define also conjugation in the Grassmann algebra. So everywhere I will assume that the conjugation of product of two Grassmann elements is by definition the product of their conjugates. So our Grassmann algebra therefore involves not only the variables but their conjugates also. And the differentiation, the conjugation is defined like this. So you swap the positions of the thetas, like a Hermitian conjugation. Again, you can also define it without swapping. Then you have some extra signs in various places, and you can map one answer to another. But it's not really necessary. Right? It's just assume this rule. That's it. So what is this? What is this Lagrangian unusual term? So this is a integral over d theta. Then we put this phi bar, so phi 0 bar plus phi 1 bar theta. So here, in this case, I assume that theta is real. Okay? So theta bar equals theta. Although I define the superfield is complex, but theta is real. So, we have a single theta. We don't enlarge the superspace. And the derivative gives phi 1 minus I theta phi 0 dot. Which is, so what you're supposed to do is you're supposed to open the brackets and pick the term linear in theta and take into account that phi 1 bar anti-commutes with theta. So here phi, for simplicity, phi is the Grassmann even. The superfield. Grassmann even complex, even superfield. And then you get minus I by 0 dot minus I1 bar. And so the action is the integral of this, and this is already a reasonable action. So this phi1 fields still enter algebraically, but this has some dynamical, at least some dynamical equations. And so this phi1 bar fields, so these fields that have algebraic equations, they're called auxiliary fields in this supersymmetric science. And one can just simply drop them, like from the point of view of the operational problem. They don't matter because their equations just set them to 0. In more general models, they will matter. They will still be algebraic, but their equations will give something non-zero. And so typically what one can do is one can solve these algebraic equations and substitute back in the Lagrangian. So one can easily prove that this does not spoil the problem. But they're a typical thing. They're a typical thing that arises in superspace. So when we write out, when we quantize and we write out the supercharge, that already implies that we have eliminated these auxiliary. So they don't arise in Hamiltonian formula. But from the point of view of superspace, they are quite abundant. And so that's why sometimes it's actually, so this superspace formalism, its main feature is that it gives automatically supersymmetric answers, supersymmetric actions. But once you're given some supersymmetric Lagrangian, if you just say started with a Hamiltonian formalism, had the supercharges, you write a Lagrangian, it's not always clear how to write it in superspace form, because superspace implies you have to introduce these auxiliary fields, and it's a priori unknown how many of them you have to introduce. Okay, so what is this action? So, well, this action, if you quantize it, you get the momentum conjugate to phi 0, which is I phi 0 bar. Maybe I want to swap the sign everywhere so that there is a plus sign everywhere. So, and then we have the standard commutation relation that phi 0 with p0 equals I. So we get that phi 0 with phi 0 bar is 1. So this is basically the oscillator algebra of if you say that phi 0 is annihilation operator, phi 0 bar is creation operator, and this is the algebra of creation annihilation operators. Why is it important? Well, because our next example will be the harmonic oscillator that we studied in Hamiltonian formalism before, supersymmetric harmonic oscillator, and we'll now write in superspace and see how it looks in superspace. Maybe it's a good time to take a 5-minute break. Okay, so let's continue to solve the harmonic oscillator language. So far we got some kind of action that looks reasonable, but it has it's like a harmonic oscillator without the Hamiltonian term, right? So we want to reinstate the Hamiltonian. So first of all, let us write out the supersymmetric oscillator in component, which we'll kind of already know. So the Lagrangian is to be I a bar A plus I psi bar psi dot minus A plus psi bar psi. Well, this is just the first term encodes the symplectic form, right? And the second term is the Hamiltonian. This is Hamiltonian, which we derived before. Now we've just written a Lagrangian for that Hamiltonian. The first part just encodes the Poisson brackets between the terms. So something like A bar equals I, and psi bar also equals I. Derived from here. So, but now we want to know how to reproduce this from superspace. So the first term we already know because it's actually exactly like this term here. So what can we do? Well, so we should promote A to our superfield phi, we call phi, and psi to small psi to capital psi superfield. But this time a Grassmann superfield, so Grassmann odd superfield. So this is even odd superfields. So from this construction here, we know what the Lagrangian is for this kinetic is. It's just this term here. So what we can do is we can write a sum of such Lagrangians, right? So kinetic term. Integral d theta of phi bar phi plus psi bar d psi. The psi is now the superfield. So here, now we want to know how to write the potential term and the Hamiltonian term. So to this end, let's write explicitly that phi is A plus theta chi, and psi will be phi plus theta b. So small a and psi are just our n psi before here, and these are the extra variables that we need in superfield. Okay, this will be odd, and this will be even. And then, well, we can imagine that the Hamiltonian term should not have derivatives because there are no derivatives here. So we can just try for the Hamiltonian the potential or Hamiltonian. And try as an integral over the theta curly h, where curly h is psi bar plus phi bar. We want everything to be real, so we take it. And well, I take this. I want to explicitly have P1 symmetry here. So I mean, this guy has V1 symmetry where you multiply n psi by phase. So here I just write it in such a way so that you can also multiply the superfield by the phase. And then, so if you just multiply these fields and take the open the brackets, then you'll find that this is maybe I'll just try the full one. So for the full Lagrangian, minus d phi. I put some minus sign because we had some annoying minus sign before, so just to cancel it. Then we decline psi bar, psi bar. And this gives us in components, this gives us I a dots, a bar, a dots plus I bar I plus I bar psi dot plus B bar B plus B bar psi bar plus BA bar psi bar. So this is a kind of slightly lengthy answer, but this is due to the fact that we have these auxiliary fields, B and chi. So these extra fields that we've introduced, they turn out to be auxiliary. They enter without derivatives. So B, B, and chi. Okay. So we can just get rid of them by eliminating them using the equations of motion. So then, equations of motion for chi and B are as follows. So they say that chi equals psi, I bar equals psi bar, B equals minus A, and B bar equals minus A bar. So and then we just substitute this into the Lagrangian. So just substitute it here. In other words, we just complete the square. This guy's it's quadratic form and B's and Chi's. We just complete the square. And we drop the full squares, and then it gives us the Lagrangian that we want. So basically, equals L oscillator. So this is L oscillator. There, you get the desired Lagrangian. In fact, one can treat superfields as the same way as we treat usual fields. And for example, we can take the variation of our super Lagrangian with respect to, or super action with respect to the superfield, just as we do for usual fields. For example, let us take this Lagrangian and the corresponding action, which is the integral. And we take a variation with respect to phi bar. We find that d phi equals psi. Right. And we take psi bar tells us that d psi equals phi. So if we act on this with d, get d squared phi equals d psi equals phi. And this is, on the other hand, this is minus I phi dot. So we get the oscillator equation that phi dot equals I phi. And analogously for psi. This is, well, these are Hamilton equations. Hamilton's equations. So these are equations of motion in first order form. So this is a Hamilton equation. Analogous for psi. Now we also want to express this in second order form. So we want to have usual second order type actions. So this is looks like the action written in Hamiltonian form. This like PQ dot minus Hamiltonian. So we'd like to also have the usual actions for the purposes of further generalizations. So how do we get the usual action with so to this end, let's split the so we have these complex fields phi and psi. We can split them in real and imaginary parts. So we'll write that phi is phi r plus I phi I, and analogously psi I. So this is a second order formalism. More exactly, we will arrive at second order formalism at the end towards second order formalism. And let us substitute this in the action. So if you write phi bar d phi term, you will see that it is phi r plus psi I. Sorry, phi I plus I phi r minus I phi I d phi r. So the first line is a total derivative, right? Because we can write it as total derivative. This is d of something squared, phi r squared plus phi I squared over 2. And this guy we will integrate by parts. So this is minus 2i, is just doubles. It just doubles. This is minus 2i phi I. Convenient for us to write them in such a way. So this is integrate by parts. And so in the psi action, it's slightly tricky, because if we do the same thing for psi, I mean, it's true that we get same terms, psi r d psi r plus psi I d psi I, plus then we get plus I psi r d psi I minus I d psi r. But here, the first term is not a total derivative because of the anti-commutativity of the fields. In contrast, the second line is a total derivative. So this is a so this is total derivative. Kind of been neglected. And the first line remains. And finally, we also need to write the potential term. So that's easy. So in the end, our Lagrangian will take the form L up to derivation by parts. So this is integral d theta. So it's 2i I psi r d phi r. Minus psi r minus psi I plus 2 phi r psi r plus 2 phi r psi r. Yes, by the way, notice also that in these superspace sections, so we want the Lagrangian, the real Lagrangian, usual, not superspace, usual space Lagrangian to be Grassmann even, of course. So we integrate over theta. So actually the superspace Lagrangian has to be Grassmann odd in this case, right? So you see, for example, if these are Grassmann even guys, this is Grassmann odd comes from the derivative and so on. So we always have to remember about the Grassmann parity in superspaces. So anyway, what we now have, the field phi I now enters as a Lagrangian plan. So imposes the constraint that I d phi r plus psi I equals 0. So what we can do now, we can express psi I in terms of d phi r and substitute it back in the action. So namely here. Yes. So what we get as a result, L, once we substitute psi I d phi r, you get integral d theta d phi r squared phi r minus psi r plus 2 phi r psi r. And d squared is minus I d over dt. Right? So we're rewritten as minus theta minus I d phi r times phi r dot minus psi r d psi r plus 2 pi r psi r. So this is actually the superspace action of the harmonic oscillator, supersymmetric harmonic oscillator in superspace in second order formalism. So this is the superspace Lagrangian. So this is L, second order form. And again, we can, as a matter of practice, we can write out the equation of motion. So we can vary with respect to phi r. So varying with respect to phi r, we get you swap the derivatives, you get 2i d phi r dot plus 2 psi r. So the 2 here comes because when we take variation, we vary further than that and integrate by parts. But I just vary this and multiply by 2. And then when we vary with respect to psi r, you get, by the same logic, you get minus 2 d psi r plus 2 phi r. Again, you can differentiate the first equation by d. You connect with d on the first equation, and then you get yes, so I d squared phi r plus d psi r, which is plus phi r, 0. And this is exactly I'm sorry, the phi r dot, right? Phi r dot, and this is exactly phi r to derivative. So we get the insulated equation for phi r, right? Unusual. The oscillator equation. Form. Okay, so let's briefly have a look and let's discuss the role of these terms in the superspace Lagrangian. So the point is that, interestingly, so they have kind of different roles. The first term and these psi r terms. So we could just drop those psi r terms for the moment, and it still leads to an interesting enough action. So if we set psi r to 0, then we get a integral of let's say L equals 1/2 integral d theta I d phi what we get is 1/2 x dot squared plus I dot. Here I write phi as x. Yes, so henceforth we will, so here phi is a real field, okay? This is phi r, this was phi r, real. So we will write phi r as x plus I theta chi. We put an I here so that this is real. Then x and chi are both real. So you see, you get an action of this form. And this is kind of, well, such actions exist in any dimension. This is just a free theory of a single boson and single Fermi. Right? Actually, you can write also in 4 dimensions, very similar actions. Just to understand how supersymmetry works, recall the supersymmetry transformation that you act with supercharge on this guy, but basically it says that delta x is epsilon pi, and delta pi is I epsilon x dot. And you can easily check that this is invariant. So basically, the variation of this gives x dot times the derivative of chi, and chi is shifted by x dot, exactly to cancel. So this is how supersymmetry invariance works. There is this guy is shifted by chi dot, and this chi is shifted by x dot. They cancel up to integration by parts. Like we said, there are no local invariants, so you always have to use integration by parts when checking. So the point is that this oscillator action that we've written actually has two different terms. So the first term is just kind of usual bosonic second order action, and psi r was completely needed to insert a potential. So this has no potential. This section has no potential. So psi r was needed to get a potential. We may ask, how about generic potential? Not the oscillator potential, but now we want the generic potential. We want a model with a potential, just like what we discussed in the first lecture, right? We have this super potential. Basically, it's pretty easy. The answer is that you should just replace here, replace 2 phi r psi r by 2. You can put an arbitrary function of phi here, right? Psi is a Grassmann superfield, so its square is 0, so you can't have any other power of psi, but you can have arbitrary function of psi with the real square. And we will see that H is proportional to W prime of the lectures before. So interestingly, this system, so once we introduce this, in particular, you could also have 0, you could set the potential to 0, but still have this psi kinetic term. And interestingly, this system has a second hidden supersymmetry, right? So we saw it in first 2 lectures or whatever, that the system with potential had actually a complex supercharge. Whose square was 0, right? And whose anti-commutator was the Hamiltonian. So I'll write it with C just to get different from usual real supercharge. So the claim is that the system also has a second hidden supersymmetry, which is not manifest. So there is a second supersymmetry, which shows up once you include this psi r term. And so the second transformation, the following. So delta 2 phi r is epsilon psi r, and delta 2 psi r is I epsilon by r dot. So this is in contrast to the first supersymmetry that acts by the Q, the operator, differential operator Q. So the first supersymmetry is kind of closed. Each of these fields is closed under the first supersymmetry, right? It's a multiple. But the second supersymmetry mixes the fields. So you cannot have a second supersymmetry without having this extra psi field. Okay? So for example, this system doesn't have a second supersymmetry, but once you insert a psi field, it does. So let us check the invariance. So you can write this also as some. You can introduce some second supercharge and check that it has the correct algebra. But let us check the invariance. So delta L. So check invariance. So delta L is over theta. And then, well, so we have to put this here. So this is 2y epsilon psi r and psi r dot. Then in the second term, we have minus 2y epsilon phi r dot d psi r. So these 2 terms cancel. And the potential term is the following pattern. So the potential term, I mean with this h function, yes? So plus 2 dh over d phi r. Delta phi r is epsilon psi r and psi r. Well, this cancels because psi r is Grassmann odd. And still we have another term, so just 2h of phi r times psi r, the delta of psi r, so this is I epsilon phi r dot. But this term is a total derivative, right? So this is a proportional to d over dt of integral h of phi d phi, right? So since like I said, h will be w prime, so this will be w dot. Total derivative. You see all the terms are combining for total derivative, so the variation is 0. Okay. So we've discovered that this system that we're studying, it has two supersymmetries, which is like we expect from first lectures. Each. So in component form, it's also useful to write it in component form. So L, you have to do these differentiations and so on. L is maybe minus L is x dot squared minus plus I dot plus I psi dot minus 2I h prime I psi plus h squared. So you see the fact that you have two supersymmetries is because you have this fermions kind psi that kind of enter symmetrical. Well, actually, I mean, this is what is called, well, sometimes it's called Witten model. I mean, this is the model of Witten paper from the 1980s. So this is a kind of Witten model in component form. So this is the same model that we studied in the first lecture. But this is, I mean, this is in superspace, in n equals 1 superspace. And we'll also later on. You can write the supersymmetry transformations of all of these fields, and they have the following form. So delta 1 x equals epsilon chi, delta 1 chi equals I epsilon x dot. Then delta 2x epsilon psi, delta 2 chi is I epsilon b. Okay, I've already written it like this. Okay, so I epsilon b. Maybe I should have, I skipped one step. So this Lagrangian, actually, if you write it in component form, it's not exactly like this. It has the form, yeah, the first terms are the same. Yeah. But these terms are not automatically like that. So this is plus b squared. So plus b squared minus 2hb minus 2I h prime chi psi. That's correct. But the point is that we have this auxiliary field B that we want to exclude, and the equation of motion for B just says that B equals h of phi, h of x. So everywhere below, we will, in place of b, we will insert h of x. So this is I epsilon b, so this is I epsilon h, this variation. And then delta 1 psi minus I epsilon b is minus I epsilon h. And delta 1b well, you can also write delta 1b, but we won't really need it. And delta 2 psi is I epsilon x dot. So these are all the supersymmetry transformations that we will need. So this is with respect to first and second supersymmetries. So you see basically the first and second supersymmetries, they differ by a swap of a kind psi. So later on when we will study n equals 2 superfields, we will see that this phi r and psi r will combine into a single n equals 2 superfield. So, now it's convenient to introduce a complex supercharge, just like we had in the first lectures, which is a complex combination of these two transformations. Yes, so we will just write the complex, which is 1 plus I2. And we introduce also the complex fermion eta, which is pi plus I psi. Then the variation, variation generated by epsilon 1 plus epsilon 2 q2. So this is like delta 1 plus delta 2. It can equally be written as epsilon chi minus epsilon bar I bar. So now we want to QC. Now we want just to consider this epsilon QC. So we combine this epsilon 1, epsilon 2 into a complex epsilon, which I will not write out, but I mean, it's clear what it is. So the point is that, so this will call delta C, variation with respect to complex symmetry. So delta C of x is epsilon eta, complex fermion. And the complex supercharge is nilpotent, so delta C of eta is 0. You can just check this using these formulas here. But delta C of the bar is not 0. So delta C the bar, so that means delta C of psi minus I psi is not 0. And again, once you use those formulas there, you get that this is minus 2 I x dot minus h of x. And now the final thing that we will do now is we want to write this variation as a Poisson brackets with some function, which is the supercharge, or just function, symplectic manifold. So you see here so it follows that our momentum dx is 2x dot, the way we've defined it. So that means that delta C eta bar is the kinetic piece of the kinetic term in the Lagrangian is x dot squared in this language plus I eta bar eta dot. So that means that eta and eta bar are canonically conjugate to each other. And I mean, this we of course write as p x dot, x dot minus p squared or something like that. So minus px squared psi eta bar eta dot. Anyway, we're interested only in this symplectic structure now. So delta C eta bar is minus I px plus 2h. This is just a rewriting of this formula. I just substitute for x dot. I substitute momentum, first momentum. And so we want to write this as a Poisson bracket with some function QC. And I mean, it's easy to guess that QC is, and similarly for x. So variation of x also should be delta C x, which is epsilon eta, would also be a Poisson bracket. So it should be epsilon times Poisson bracket of QC with x. So it's just by looking at these formulas, it's easy to guess that QC is proportional to eta and minus IPX plus 2H. Because, well, so x and px is 1, and eta bar is also 1. I. So once you compute this with eta bar, you get the you get maybe it should be eta I eta or something like that. You get this answer, and the point is that upon quantization, when we replace the momentum with the derivative, and eta becomes our fermionic oscillator, fermionic creation and annihilation operator. So this is upon quantization. We replace px by minus I d over dx. So this becomes QC equals I eta minus d over dx. It's 2h vex. And well, this is exactly what we had in the first lectures, right? We called eta, we called psi, but here we call eta. And 2h was w prime. That's the right relation that, well, 2 is just some normalization. And so we have recovered that model from the first two lectures by kind of directly quantizing this n equals 1 superspace model. So we rolled the n equals 1 superspace model in components, eliminated the auxiliary field B. Then we passed the Hamiltonian formalism. We deduce the supercharge, we quantize it, and we get that supercharge we had before. So this is kind of the general logic that one can follow in superspace. That's the relation between the approach of the first lectures to superspace approach. And later on, we'll develop the superspace approach to more general models. So next time we'll do sigma models in n equals 1 superspace. And then we'll pass to n equals 2 superspace and see how, for example, how this superpotential naturally appears in n equals 2 superspace. That's why this will explain why we keep this W prime. So that's it for now. Any questions? Yeah, maybe the thing that you should observe that in n equals 1 superspace, this potential to write this potential is not so trivial. It involves this psi field and some funny coupling. It is what it is. In n equals 2 superspace, it will be a little bit more simple, maybe. Yeah. Because these fields will, unite in one multiplet and so on. But for sigma models, n equals 1 superspaces will be fine too. Okay, so no questions then. See you on Tuesday.